So stable equilibrium, once again, where it's going to be able to hold this position. Unstable, it's going to typically have issues with falling over. And then we're going to have the neutral equilibrium, where that's where we're going to talk about being able to roll something. And not just do we have linear stability with its being able to stay in its displacement and then not be able to, we're going to have rotary stability. And that's going to be our ability to resist the rotation. Now, when can you guys think about in sport or otherwise where you can have issues with rotary stability? Baseball, there you go. So when we're rotating, we're swinging the bat. We're going to be rotating throughout that axis. Same thing with softball. I'm sure you guys have seen somebody swing and miss the ball epically and nearly fall over because they did not have that rotational stability. Good. Now, there's a number of things that we're going to be able to do to help enhance our stability. First and foremost is just increasing the size of the base of support. So literally, that's going to be getting our feet set out wider. So we're going to be able to now absorb a little bit more force going side to side and keep ourselves balanced within the center. Now, having your center live of gravity within that base of support is an important factor to stay balanced. So if you guys are home, go ahead and try to stand up wherever you're at and then try to have your center of gravity outside of your body, and you're going to have to fall and or step whatever direction that goes. So as long as my center of gravity is in between my feet, I'm going to be able to keep my position. Now, the next component, and you guys have probably felt this before playing sports like football or otherwise, but the lower your center of gravity, the easier it's going to be for you to be able to hold your position, along with obviously if you have a greater amount of mass. So that's getting back to momentum and inertia. The larger bodies are much harder to move. Now, if you know a force is coming towards you, you want to go ahead and shift your center of gravity towards that oncoming force. That way, when it does come into contact with you, it's going to give you a greater base of support to go ahead and try to absorb the blow. And we can always extend our base so we can step our feet out wider so that we're going to not just have that line of gravity towards the force that's coming in, but on top of that, we're going to be able to, once again, have a greater ability to absorb the force. So, well, how can we figure out where this is? Well, we can literally look at the distribution of mass. And this is where we can do things like try to ballpark or literally weigh each segment of the body. And then from there, we can figure out, well, where does that center of mass naturally occur given the center of mass of each of the segments, the length of the segments, and the location of each of those segments. Because it turns out gravity is uniformly pulling everything straight down. And as you guys have had a chance to do in the lab a little bit, is we can use those force plates. So whenever we did the postural sway lab, so the lab where you guys stood on the force plate with 1 foot on each force plate with your eyes closed, which you guys never got to do because this happened before the lab shut down. Oh, shucks. How many of you guys have had a chance to watch that video? Not yet. It's okay, Sam. Any of you guys had a chance to do that yet? Okay, well, we're going to find whenever you guys watch that video is you're going to see the natural sway, how we tend to just typically shift our weight a little bit side to side, and that some of us are going to be able to, are going to naturally favor one side of the body to the other. And now this is really useful because we can do things like vertical jumps, and we're going to look at not just the takeoff and the landing force on the force plate holistically, like you guys have had to do for another lab, but we're going to actually get to see, are we favoring one leg over the other, which in turn is going to be showing us that asymmetry that we have in the body. And if we're not careful, that can set us up, will definitely increase our risk of injury. So any questions about basics of stability and center of gravity? Thank you, Sam. So let's talk a little bit about drag. Now, everything we've learned up until now when we've looked at our physics is doing it in a vacuum. So we literally don't have to deal with any type of wind resistance, which it turns out we do not live in a vacuum. And we need to understand how the flow of not just liquids, of fluids, but gases over the body, over objects in motion are going to influence their flight, both pattern and distance. So when we're looking at a object moving through a fluid, okay, we've got not just water or air pressure, which is naturally around us all the time, but we also have water pressure. And obviously that water pressure increases pretty rapidly the further down we go underwater. You guys naturally can't always really feel the air pressure around you, but it's there. You can definitely tell a little bit more whenever you go up really high in a building, like in an elevator, or go up a mountain or fly in an airplane, where your ears pop due to that change in air pressure. Now, we're going to find that not only do we have that pressure that's surrounding us and resisting our motion, but we're also going to have a buoyancy factor, which is then coming down to the density of the object compared to the density of whatever fluid is around. So we as humans obviously don't float in air. What could naturally float in the ambient air? Bubbles. Now, do bubbles float, Cameron, or they normally tend to come back down? That's true. They pop eventually. All right. A balloon with helium, exactly. Because helium is going to be less dense than the air around us, so that's going to go ahead and float off. Okay, and then the same basic principle of a hot air balloon. Only whenever you heat the air, it causes the air inside of the balloon to have a lower amount of density than the air around the balloon, which eventually is going to not just pick up that hot air balloon, but then the basket underneath it. Now, the same is true of water. And obviously water has an interesting property in that its density is pretty close to the density of a human body. However, what is, do all humans have the same density? Exactly. So humans don't have the same density. Individuals that are leaner have typically more muscle mass and less fat mass. Muscle is a tissue that tends to be denser than the water around it. So that's going to cause it to sink. Same thing with your bones. Your bones are denser than water, they're going to sink. Whereas fat, as any of you guys have ever had to wash the dishes and you saw fat droplets on the top of the water, or just in the act of cooking, you can tell that water is is denser than fat. So individuals who have a higher percentage of body fat can float in water. Now, salt water is denser than fresh water. So that's why some folks can float in salt water, but they can't float in fresh water. Have any of you guys ever heard of a sensory deprivation tank, sometimes referred to as a float tank? So a sensory deprivation tank is really interesting. It's effectively what would be almost like a giant bathtub. There's only about 8 inches of water inside of it, but it literally has so much salt water inside of it. Or not, sorry, salt water, but actually it's magnesium sulfate, aka Epsom salts, that literally anybody can float inside of it. And I think it's usually about, ends up being like a ton, literally a ton of Epsom salts inside of this tub that is, it's big enough that an entire human being can lay down inside of it and not touch the walls. And, part of it is literally the temperature of the water is meant to be close to body temperature. So you don't have much of a sensation of temperature around you. You close it so it's completely dark in there. There's no sound, and hence the sensory deprivation concept behind it. And the buoyancy of how you get that for any human is you just massively jack up the density of that water. Now, how many of you guys have heard of the term drag before? How many of you guys have heard of drag? All right. Austin, I'm unmuting you. Just give us your best definition for what drag is.
Is it like the wind that kind of pulls back, like from an airplane or something, as it's going through air, kind of like the...
Yeah. We get drag in both liquids and gases, but yeah, it's the resistance that whatever the media you're going through is giving the object to go through it. So exactly. Nice job, bud. Nice job. So when we're looking at drag force, we're going to see that it's always relative to how quick you're going. So hence, any of you guys have probably felt it before whenever you're just standing outside on a day where there's no wind, and then you went from a walk into like a top speed, sprint where you can feel that wind resistance against you. And that's the drag, because literally your body is not perfectly aerodynamic. So there's a lot of that wind molecule that's effectively stacking up, and you're having to push it out of the way of your body as you're moving forward. And that resistance that it's giving you is what's known as drag. And obviously that drag is much greater in water, where you can literally feel it pushing up against you. Another easy way to feel drag in air is if you guys are riding in a car and you put the window down and keep your hand even with the wind, and then you let it come up, and you can feel all that resistance pushing up against your body. Now, the surface drag is effectively going to be how much is going up against you given the surface of the object that's going by. Now, the more streamlined we are, which means effectively our form drag of our position in our body, the better or more efficient we're going to be able to move through, the less drag we're going to have. This is why, thank you, Tyler, individuals that are riding on bikes at high speeds typically tend to bike in that very extended bent over position as a means to decrease their form drag. So I'm sure all of you guys, if you've ridden on a bicycle like down a hill quickly, you've bent forward to decrease that wind or that drag because of the form of how we're moving. It allows us to move faster. And then you guys ever had the poor luck of trying to move sheetrock or drywall on a windy day, and unfortunately lined it up with the wind for just a second and nearly got yourself knocked over? Well, I guess I'm the only one that has made less than optimal decisions before in that arena. Now, another thing to keep in mind is what's known as wave drag. And now waves is going to be what you think is literally the wave going over or around your body. Now, it's easy to think about that in water, but whenever we're moving through with wind, you're going to naturally have that wave drag created a little bit, which creates, I don't mean to use the term turbulence in the perfect sense of like flying in an airplane, but instead, getting back to the driving example, how many of you guys have ever driven in a small car and gone and been passed by a semi or a really big vehicle, or you've been trying to pass that semi and you can literally feel that kind of the shimmying that the car does due to the wave drag that that semi is creating as it's plowing through the air around itself. Bingo. So anytime we throw an object, anytime we move an object, it's going to have that drag that's going to be effectively influencing its motion. And what we're going to find is that we have got not just lift, because that's going to be a component of literally the force lifting the object due to the aerodynamics, or just the, I guess you could say literally the form that it has going through, that's going to cause it to rise up. Now, when we think about lift, you think about airplane wings, where because of its natural incline, it's going to be pushing X amount of the air down, and the rest of it's going to sweep over. And because of the curvature of the wing, also push itself down to a lesser extent, which in turn is lifting the body of the airplane as it's flying through the air. Now, when we're talking about the same thing in water, you can be talking about hydrofoils. If any of you guys have ever done anything like water skiing or otherwise, I'm sure you guys know that you have to keep your toes up. If you put your toes down, you're just going to eat the water really fast. And it's going to be, you're not going to have a great time. And that's going to be due to, once again, the forces that you're producing. And that's also, you know, when you're swimming, you're pushing the water down to a certain extent, especially if you're not buoyant, so that you can keep yourself from going all the way, really sinking to the bottom. Now, whenever we're pushing ourselves along, specifically in water, we're creating what's known as vortex propulsion. So if you ever watch a canoe paddle in the water, even your hand going through, you can see just this little spiral on either side of your hand or either side of the paddle. That's because you're pushing a solid amount of that water molecules behind you, but some of them you're pushing and they're also falling off the edge of the paddle as they're being pushed, which is causing them to naturally spiral and create what's known as vortices. Now, vortices is effectively that swirling that we're going to have. If we go ahead and do the same thing with moving air, that's where we're going to have that disruption. But we can specifically utilize this when it comes to sport to throw something like a curveball. Because literally what we're doing is the seams on the softball, on the baseball, when they're rotating at high speeds, are literally going to be pushing the object or pushing the air around it in that same spiral pattern. But what it's going to then do is effectively, it's going to create a lower pressure gradient on one side and a higher pressure gradient on the other. So if you have a right-handed pitcher and they throw a curveball, so they rotate that ball to the right, the seams are pushing the air down, over, up, and over. So what they're literally doing is they're creating a lower pressure gradient on the left side of the ball. So if I'm right-handed and throwing it, and it's creating a higher pressure on the right side, so pushing it down over here and up over here. So what that's going to do is literally cause the ball, if we have enough rotational speed and enough velocity, creating enough drag, it's going to literally displace enough air that eventually the ball is going to start to shift down and to the left from the thrower's position, or from the batter's position, it's going to be coming again down, but across and to the right. And that's literally caused through this production of this drag, which is referred to as the Magnus effect. Now, the same thing is true about the rise ball in softball. And specifically, Sam, if you don't mind unmuting yourself, do you just explain the basics of what a rise ball is?
It rises through the zone.
Is it kind of like a fastball, but it kind of lifts up as it comes towards you, right?
Yeah, so like when it comes towards you, it looks like a really good pitch to hit. And then once you start to swing, it just goes up so that you completely miss it.
Nice. And which way does the pitcher rotate the rise ball?
I have no idea. I don't I don't pay attention to pitchers.
Well, it's time to start being a better student of your sport. Okay, So, no, that's all right. It's all right. So what we're having to do here is we're having to create a greater pressure underneath the ball and then a lower pressure above it. And so since the ball's moving forward, if the seams are rotating essentially backwards towards us, so what that's going to go ahead and do is the seam is pushing the air down, in front, above, and behind. So it's getting a lower pressure behind the ball and a higher pressure in front of the ball. So eventually that backwards rotation is going to cause that ball to get a little bit of lift. Mind you, that drag is also slowing it down. So it's going to, if it wasn't for the fact that the pitching mound is only 45 feet away, and it's typically being thrown by very tall women with long legs that are probably releasing that ball and closer to probably more like 40 odd feet or even shorter, it's an effective pitch, but it's not going to be one that you're going to be able to, cause that ball to lift so much that it's going to fly out of a stadium. So, but all of that is due to the Magnus effect. Any questions there, guys? So let's go ahead and talk about the drag equation, okay? Now, the drag equation here, guys, and there's a nice little YouTube video if you guys want to click on the slides, okay? So what we have is the total amount of drag is going to be equal to, first and foremost, the coefficient that's going to be important with everything that's going on, which we're talking about the temperature of the air, the humidity, the air density we're going to get is going to be coming down to barometric pressure. Velocity of the object, obviously, is however fast it's moving through. The reference area, which is going to be the actual area that's going through the air. So there's a big difference between, as a human body standing out wide and having as much resistance as possible, and then being streamlined trying to go through a medium. And that's going to allow us to, in theory, produce the same amount of drag, but potentially be able to go faster. Because at the end of the day, why is it that, it sounds odd, guys, why can humans only run so fast? Why can't human beings run 60, 70 miles an hour? But I was gonna throw in the protein powder and some peanut butter again. If you want to try to do some mad science. Oh yeah, I'm enjoying the silence. By enjoying the silence, I'm not. Can you only generate so much force to move themselves? Now that's true. We can only do a finite amount of force, but the big issue with top speed sprinting, Blaine, is the fact that you're literally, when you're trying to sprint as fast as you can, the drag going against your body with every stride when your leg's off the ground, when you're flying through the air, is slowing you down at the same ability that you're trying to push against that drag to speed yourself up. So if we could somehow give you like a super light space suit, for lack of a better term, and have you sprint inside of a vacuum, you would actually be able to go a lot faster because you wouldn't have to deal with that resistance. Does that make sense to you guys? Drag is literally slowing us down all the time whenever we're trying to move through space. Good, thank you guys. So now when we look at this formula, really, what's the only thing that we can control in there that's going to help us with our drag? What's the only thing that we can really control there? Good point. Good point. You can control your velocity. Yeah, you can always choose not to move. Okay, but we can only get our velocity up to a certain speed. At a certain point, we're not going to really go any faster. So what's something that we can make choices with to help enhance our speed? And I'll say from the perspective of maybe riding something like a bicycle. Bingo. The area. So the reference area that's going to be actually affected by us traveling through the medium. Now, when we're looking at this formula again, of all the variables, which one has the greatest influence on how much drag we're encountering? Meaning, if we just increase it by 1 point, which is probably going to have the greatest effect? Excuse me, greatest effect. Now, the reference area is still influenced by essentially however much, square meters that we're having that's effectively causing the drag force. It's actually the velocity, because we're really experiencing, when you're standing still, you're not really experiencing any drag. It's as we start to move that we're going to be increasing our drag. And notice it's the velocity squared. So once we start moving, that drag force increases massively, because if we're going 1 meter per second, well, 1 meter per second squared is 1. 2 meters per second squared is 4. 3, 9, 4, 16, 5, 25, 6, 36, 7, 49, 8, 64, 9, 81, 100, 100, 11, 121, 12, 144, 13, 169. Guys, do you guys want to say something, or am I just going to keep talking to myself? No, but keep in mind, guys, it's important that we understand both the velocity and then the area when we're talking about drag. Now, some other factors that are influencing this is going to be the air temperature, okay? If the temperature is higher, your total amount of drag is going to be lower. If the air pressure is higher, the total amount of drag you're going to encounter is also going to be higher. And then finally, the more humid it is, the lower drag resistance you're going to have. So what we've got pictured on the right is just showing kind of that air displacement of different objects and how they're going to create what's known as a turbulent or a non-turbulent wake, and hence why aerodynamics matter. That's why, if you notice, most cars, yeah, there's a little bit of difference in how the grille looks. There might be a little bit of difference in the contours in the hood, but most cars these days look incredibly similar because they're all trying to exploit the aerodynamics to the best of their ability. So with that being said, that sums up our wonderful talk about stabilities and drag. What questions, comments, concerns do you guys have that I can go ahead and field for you guys?
Are we going to be using that drag formula a lot?
You guys want to?
I mean, maybe in a simple context.
Yeah, well, we can do a couple simple problems with it, but we're not gonna go that hardcore with it. How does wave drag relate to velocity? Okay, so the greater speed you happen to be producing, the greater amount of wave drag effectively you're going to be experiencing and or producing. So Kylie, think about a boat on the water. If the boat's barely moving, it's barely creating a wake. It's barely creating these waves. Now, the faster it's going, the greater the wake you can see that it's generating. So the same thing is going to be true about that media. So the greater the waves, the greater the drag you're having to go against. Blaine, it's going to be the same basic way we solve most of these problems, where it's going to be, you'll have all of the elements you need to solve it. So you'll be given your coefficient, your density, your velocity in your reference area, and you'll have to then figure out what the total amount of drag is. Or you're going to be given, the drag and everything except for the velocity. Something where it's, you're only really solving for one variable, but you're going to have to think your way through it. Awesome. So wind resistance is going to be more, we can be talking about an object that's going to be stable or holding its same position. Drag is going to be the total amount of resistance that object is encountering, also based on its velocity. Because as you guys know, your velocity or the drag that you're going to be encountering is relative not just to the speed that you're going, but also the speed of the air around you. So how many of you guys have ever tried to run into the wind? How good does that feel? Yeah, not good, not easy. Now, when the wind's at your back, that can be great, especially if the wind is going at 20 odd miles an hour. And Lord knows I'm not running at 20 miles an hour pretty much nearly ever. So that's helping push you along and allowing you to go even faster because you're not having to deal with that drag going against you. Does that answer your question, Haley? Anytime, guys, anytime. Okay, vortex is going to be that swirling, okay? So next time you guys have got like your sink full of water when you're hopefully washing your dishes, because hopefully none of you guys are going full-blown like sad bachelor mode where you just have like sinks full of dirty dishes that never get touched. Put your hand in the water and just push it across. And if you really watch your hand going through the water, you're going to see a natural swirling occurring on either side of your hand. And that's going to be that vortex because most of the water molecules are pushing with you, but some are sliding off the edge on either side as your hand goes over. And when they slide over, they're going back and then pushing the other molecules up and around, which in turn is creating this vortice. So vortice is just a little spiral, a little whirlwind otherwise. Does that kind of make sense to you, Kylie? Okay, good. Because anytime we move through media, we're never 100% efficient because we're going to always have to have that, wind literally breaking over or moving around the surface of our body, the surface of our car, the surface of the baseball as it's going through the air. Now with better aerodynamics, we get lower drag, it's easier to go faster. That's why speed cyclists have those specialized long helmets. They get themselves into the more forward-leaning positions. So they're going to be in that better position to not just to effectively deal with less drag so they can go a bit faster. Now, obviously, if you're just riding a bike around, you can be more of an upright position, mountain biking. Same thing as me, a different position so you can balance a bit better because you're not trying to worry about those maximal drag resistance. In fact, in thinking, you will want a certain amount of drag because it's going to slow you down so you don't become a high-speed organ donor. So it's important that we understand these concepts in more of the theoretical. You can kind of think your way through it, kind of how this is going to influence an object, especially when it comes to literally things like throwing a curveball. Because when something is rotating, it's going to be influencing its own sexual flight pattern because of that higher pressure and lower pressure being created on one side of the ball compared to the other. And so making sure that we understand that, how when objects move through air or water, they're going to disturb that air or water, and then that can have its own little influence. And then things get pretty damn insane when you start to look at objects that are going faster than the speed of sound, because literally breaking the sound barrier is literally moving so fast that no longer are you pushing the air molecules out of the way, you're just ripping through them because you're moving faster than they can actually distribute. That's why the first number of people in airplanes trying to break the sound barrier due to not perfect aerodynamics and otherwise of those jets, they unfortunately perished because little aberrations, whenever they broke that sound barrier, it's a lot of force you also have to come through with and have to tolerate, for that matter. Any other questions, comments, concerns? We're familiar with the boat trimming angles, and how does that relate to drag? Boat trimming angles. What is that, Cam?
So like if you take off in a boat and you're going a particular speed, like there's a way to trim an engine to where it makes the front end of the boat set up or like set down.
Mm-hmm.
I'm not that educated about it either. I'm just kind of.
Well, I do know that there are some, obviously there's some boats that what they have is like a hydrofoil and otherwise, so that's gonna be less amount of the boat literally in the water, having to deal with the drag of this going through the fluid. I think it's like hydrofoils and otherwise is what they're referred to as. So like anything else, yeah, if you can have less of the boat in the water, you're going to have less resistance, because it turns out your drag you're getting from moving through water is way higher than the drag you're getting from moving through air. So I imagine, like anything else, the aerodynamics, for lack of it, some fluid dynamics of what you're trying to have for boats are going to be far, far better than the type of dynamics that you're going to have for things like, like you look at something like a, canoe, kayak, all boats tend to be, trying to have the best dynamics they can going through the media. You see that's why barges naturally have a greater amount of resistance, but they kind of want that. So it makes it a little bit easier for them to control and move because they're not, easily slipping through. So like anything else, how you position the object, how it's oriented is going to influence, hence why boats, when you think of like your traditional where it's kind of got the rounded front hold and a flat back, that's why it's a lot easier for them to go forward, but going backwards is a lot slower, but that also tends to be where the engine mounts are. So kind of just naturally taking advantage of those properties so that you're going to be able to move it faster in one direction than the other. And then at the same time, if you think about it, because of the hull is that longer body, that's why boats move well straight forward. But at the same time, when a wave comes and hits them from the side, there's a lot of resistance to being moved because of the drag they have going in that lateral direction.
So if you had say that like your boat's setting out of the water at a certain angle, then you would be dealing with drag of the water and drag of air, right? Like drag of air resistance.
Yes, yeah, because you're definitely having to deal with the air resistance going over the object. But the key is when we're talking about things like a boat compared to obviously like, you and I running on flat ground, well, that drag matters for us. But if you were to be, I don't know, standing on top of a tractor trailer, yeah, you'd still feel that resistance, but at the same time, it wouldn't be anywhere near as bad because it turns out you as a human, you don't, the object you're riding on, that's the one that has a massive like magnitude of size compared to yourself. And so that has a greater area that's being influenced, and not to mention the mass that's giving it that inertia and momentum that it has to be overcome in order to get it to go faster or slower. All right, folks. So the last thing I got for you guys today, and I'm going to walk through it with you guys right now, is, so I've been, and Cam, I did get your email. I am going to get back to you with a training program. Give me some time, because I've been putting my energy outside of death by grading into this thing, where what I want you guys to go ahead and do is you're going to link over videos in the public domain for the exercises and add in any exercises in a changed font color for me to add to these indexes. So effectively, the one that I've got for you guys is based on the more recent one. So what you're going to go ahead and do is, you can find literally a video of someone doing push-ups with bent knees. So what you would then do is go over, hit insert. You're going to go link. That's where you would paste in your link, then hit apply. And then once you do that, you're going to go ahead and go insert comments, and you'd be like, done by, insert name. And for each one of these that you insert on this document, that's going to be 1 point of extra credit. So effectively, what I've been trying to do to put together for folks is they can go ahead and come on over here. Since I know a lot of people are stuck at home, they can pick whatever exercise they want to do. This is just the rest period. They can put that in there, giving somebody like a rep range that they're trying to work within, giving them the resistance that they're going to be working against. And so from there, they can go ahead and enter in these values and go ahead and follow this training program. Because it's also kind of cool is, let's say, this person, how many squats they actually did was 12. And then it's going to actually give them goals of how many they should do the following week. And so they can go ahead and it, in theory, auto-regulates. It's a bit aggressive. But then what's also cool is then you can come over here and rate your soreness, which is going to then influence the how fast you're going to be and adapting your training program. So it's got a lot of functionality. I'm still, cleaning up all the bells and whistles on it, but really just trying to crowdsource through you guys also ways to make it a little bit better. For folks, what's actually fun is the underpinnings of this program is actually things that you guys can use for your own class, and that we've got the center of mass. So this is what you guys can use or should be using for your own project, where I was breaking down based upon the mass of the individual, given just averages, and looking at then resistance from peer reviews of what percentage of body mass individuals are lifting against when they're doing push-ups. And then mind you, notice there's error variance built in, so it's not perfect. But we've got that information so people can go ahead and literally write in their mass of the objects. It's got a couple different references that you guys can use for the center. Then this is just my math stuff. We use the force plates. Okay, I'm going to be vain. I use the force plates to literally figure out what the resistance is when you're doing band resisted push-ups. So it's got literally how much resistance depending on what your displacement is over a fake human, which was kind of cool. And then the same thing with standing on bands, and then obviously I made it cumulatively a little bit higher, and then based it on the midpoint of the range of motion as opposed to the top where it's going to be the heaviest. So pretty happy with how it's coming together so far. Definitely a lot of things to break down, but now you guys have that link also on your Blackboard, so you're going to be able to go ahead and put that stuff in there. And like I said, it's just going to be, for extra credit. You guys have got the walkthrough for it because we've just talked our way about it. If you guys have questions, go ahead and let me know now. Otherwise, yeah, how are you guys' projects coming along? Coming along that good, huh? Thank you. Sydney, how's yours coming along?
It's okay right now. We've been working on it a little bit, so
Okay, you've been
I
able.
need to film the video here pretty soon.
Okay, have you been able to get in contact with everybody in your group?
Yeah, we've been in contact.
Good. Yes, Kylie, remember you need to write your paper over your joint. So that's when you're going to really give me the information on the force, the torque, the rotational velocity, the rotational acceleration. You're going to have at just your joint, along with the muscles that are being used. Your guys' presentation is only going to be breaking down the differences between what's going on between your expert and your novice. So kind of like, what are the key differences? So your part of the presentation might literally be the expert and the novice did the same thing. You know, they did these basic movements. Maybe the expert did theirs a little bit faster. So they produced a little bit more power, a little bit more acceleration. But otherwise, like, yeah, it was the same. Others may be like, you know, the difference between, you know, shooting a basketball and like, okay, they did a lot of things very different there, and you can go and break those down. So good question. What other questions do you guys have on your paper and presentation? Now, for your presentations, guys, we could zoom in and then have you guys share screen and have somebody go through it. I'm not opposed to that. I personally think that is an option, but at the same time, I don't know what's going on with your guys' life. As you can tell right now, we've only got 12 of you, and at our peak number, we had 13. Obviously, there's a lot of stuff going on in everybody's lives right now. I'm not trying to punish anybody with work. So what you guys can do, if you're not familiar with it, is you can go to slideshow, and then you guys can record slideshow, and obviously you do that from the beginning. You would have it so play narration, use timings, and show media. And then you can send that around. I think you can do the same thing from doing it on a Google Doc. Or you can always just literally, you know, cut it down so your presentation is just your slide, save that slide, and then email that all to one person who's then going to go ahead and, you know, put that on the interwebs, or go ahead and, you know, save that in one way or shape or another and give that to me. And then I'll put your guys' presentations up on Blackboard so other groups can go ahead and see it. And I will obviously go ahead and be grading all of your guys' presentations, but I'm also going to allow you guys to have other individuals give you feedback on your presentation, which is really just meant to be another way to kind of, you know, buoy up everybody's grades and not really punish them with it. So, but, you know, since we're obviously getting close to the end of the line, and literally this was the last lecture, yeah, we're going to start trying to do these presentations coming up in the next week or two. Yeah, literally we're going to have them start next week on Tuesday. Any questions, comments, concerns? Tyler, how you doing, man?
Doing great.
Boy, that sure sounded like enthusiasm.
Fantastic.
I take it you're back home also?
Yeah, I'm back home.
Dad putting you to work?
Yeah, I've cut down about 20 some trees in the last 3 days.
Now, what do these trees do to you?
Apparently they're in the way.
Of what?
I don't know. It's my mom.
Uh,
Mom says they're in the way.
So I'm glad to hear you're doing okay. Sam, I'm still going to be having classes per the usual on Thursday morning, and, you know, answering any questions and probably just trying to help people out with their presentations in whatever capacity that I can. But yeah, otherwise, I'm still going to have the lecture just so I have something that's effectively more consistent for my own schedule and or sanity, that I'm still going to be, teaching whoever shows up, or at least answering questions from whoever has it. We don't obviously need to go the full time. We'll be done in just a couple moments, but just making sure that resource is there for you guys. And then kind of the next week for the presentations, I mean, if you guys really want to try to Zoom the presentation, we can do that. Otherwise, we can go ahead and just plan on, you guys send the presentation to me that way. I'll grade them and get back to you guys, along with obviously grading all the papers. Yeah. Any other questions, comments, concerns, guys?
Is there a specific due date for the presentations?
Yes, they are going to be due effectively on this upcoming Tuesday.
Okay.
Mm-hmm. Can you email the presentation to me? Absolutely. And if we have any issues with it, obviously I'll let you know. I believe there should be a tab on Blackboard that you can just submit your presentation. And then obviously the grade's going to get copied over to the other people in your group, well, for what they did with their section. And that's where I prefer to have you guys send it in, just because, our email inboxes only have a finite amount of file space, and those can be pretty big. If we send the presentation, do we have to record it? You guys got to have some type of narration over your slides. So remember, we want you guys to have your information on the slides. That's really important. I want you guys to go ahead and obviously have your videos of your individuals performing. Your best bet is to turn it into a GIF. So you can utilize what's known as Giphy as a means that you're going to be able to go ahead and show that those exercises and those movements. So give me one moment. I've got like a lot of stuff on my screen, so it makes it really hard to see what the heck I'm doing. But so this is one that we did for partner carries and movements. Me and my old GA. Here we go. So we have GIFs of individuals doing these movements. So you've got this that you can use for explaining different objects, and you're going to be trying to do the same thing. And I literally just created these on Giphy using the original videos. So for the extra credit, we were supposed to add the link to the exercise already there, or add a whole new exercise. Either option, Bailey. So you can either add in an exercise that isn't there. Now notice these are all body weight calisthenic exercises that you can sometimes add a little bit more resistance. The basic idea is talking with the strength coaches. A number of them were talking about how they were having issues with, like, how do we program for these kids while they're back home and they're going to be able to train and stay in shape. And they, it's difficult since obviously most of them no longer have access to a barbell. So it's like, okay, given what we can break down, looking into the resistance you're going to be actually encountering relative to your own body mass and otherwise when you're doing different exercises, then okay, if we know when you squat, you're lifting 88% of your body mass because you're not lifting your knee, you're not lifting your lower leg, and you're not lifting your foot. And for most people, that ends up being about 12% of the body mass. For people with really small calves like me, it's probably more like 6% of their body mass, but I do have really big feet. So that probably helps and kicks me up to like 8%. There you go. My wife's at least giggling at that concept a little bit. So from there, what I'm doing, I've got, that's why it's the percent of your body mass lifted. So notice when we do like a one arm push-up with our feet flat, we're actually lifting 128% of our body mass, because now we're looking at relative to that single arm, which before would have just been 64%. But now, well, 64% doubled over on one side. That ends up being a pretty decent resistance if we want to think of it like a bench press. So the idea is people can plug in, and Tyler, I'm going to be sending this out to the cheerleading team and the dance team pretty soon. It's just a way for people to hopefully try to stay in shape while they can exercise. And that's why it's up here for you guys. Feel free to use it if you got friends that are looking for some type of program that they need just to kind of help them maintain sanity. Please, just send it to them. Tell them they're welcome. Tell them to feel free to, donate to the EKU XFIZ lab. We can always use more space if you guys didn't realize that coming in, obviously, back when the world still worked. But yeah, so if, I put in the things that I know, so like bodyweight low rows and variations on it. We've got pull-ups and variations on it, like little extra things that, like I'm familiar with and we use pretty frequently. But if you guys have got some type of, bodyweight calisthenics, this is upper body pushing, this is upper body pulling. This over here is lower body exercises. And I got to reorganize that between single leg and double leg. Then we've got core exercises. Notice I don't have that many listed because if you need more than hanging leg raises, planks, and probably V-ups, you're probably doing it wrong. Then we've got other things like lower body accessories. So this is like, the glute bridging and other nonsense you see people doing on occasion. Upper body exercises, and then some plyometrics. And I still, I've added in some things for programming and otherwise. I still need to keep entering and updating this as I go through. But yeah, if there's some type of lower body or upper body exercise and you can actually link to it. So you can be like, oh, I like this exercise. And like, okay, like that's what that is. Like, okay, that's a good choice. Like, awesome. Then go and put that on there. But, make sure you link to it so I can see the video. Because I might look at the video of it and be like, okay, that's an interesting idea, but it looks like people might naturally select themselves. Meaning they might hurt themselves, and I don't want anybody to hurt themselves on it. I just want them to have something to help them, get through it and feel like they're doing a program that is actually, based on reason and trying to progress according to what people are actually capable of doing. So, yeah. I feel like I might be talking in circles there. So, any other questions, comments, concerns?
Is there a page like how long the paper has to be, or is it just as long as all the information's there?
As long as it takes. Most folks that do it right, because they put their math in there by putting them in like tables, or sometimes they'll just do like screenshots of their handwritten math into the Word document. It ends up typically being usually at least 4 to 5 pages, especially when you're adding in references. Yeah, there's no minimum. The maximum I'd say is 10 pages because, good Lord, if you can't get it done in less than 10 pages, you're just really making me do extra work, maybe out of spite, which I can respect that. Spite is one of my favorite emotions. But hey guys, when in doubt, my goal is the same goal it's been this entire semester, which is I want you to do well. So if I'm not going to straight up tell you like, oh, like this is exactly the grade you're going to get, but you guys can always email me up until effectively Tuesday morning at 9:30 a draft of your paper and be like, how's this look? And I'll be like, yeah, it looks pretty good. This is probably a B right now. You should probably work on this. You need to work on this, this, and this. Or I'll be like, yeah, this is good. You're going to get an A. You just want to submit this now and save us both some time? Because I've no worry, no interest in that, because I know you guys are trying to do your best and it can be hard. Yes, the rubric's up there, so you can see that on what I'm looking for. But, we're not obviously doing the same in-person conversations like we once were. And, I've obviously made a number of comments about how I don't enjoy the mild awkwardness of doing this over tele conversations. But, we're all just trying to do our best. So how much of the final grade will depend on the presentation. Your final grade for each of those ends up being about, I think they're both worth about 50 points, so it ends up being 100 total. So it ends up being almost, a little bit less than 10% of your final grade, because the semester ends up being out of about 1,100 total points.